In this video, we're going to work through 6 kinematic problems. Question 1. Car A is d meters ahead moving at constant speed v sub a. Car B follows faster at v sub b is greater than v sub a. How long until B catches A? We're going to start by using a position versus time graph to describe what's going on. Both objects are moving at constant speed, so you'll notice that the graphs are straight lines for both objects A and B. Notice that A starts higher up on the position axis because car A is ahead of car B. And we want to find out how long, what is the time it takes for car B to catch up to car A. So we're looking for the time to reach this location. For constant velocity, we can use final position is equal to the initial position plus the velocity times the time. Now let's start with car A. Car A is a distance of d ahead of car B. So the final position of car A is equal to d plus VA times t. So this will tell you the final position of car A, which is a d distance ahead of car B. Now car B will have a final position that is equal to VB times t. Now what we're going to do is we're going to combine these two. We're going to set them equal to each other, and then we're going to solve for t. So we have d plus VAT. This is the final position. This will give you the final position for car A. And set that equal to VBT, which will give you the final position for car B. And notice that the t is, we can factor out the t. We're going to get the t together and factor that out. Here we have the t that is factored out, and we're looking for t. So we're going to divide both sides by VB minus VA, and we get that the time is equal to d divided by VB minus VA. Question 2. A ball is thrown straight up with a speed of v naught and an acceleration of negative g. Find the maximum height above the release. So here's a dot diagram of the ball going up. Notice that the velocity decreases on the way up. This is a velocity time graph. The ball is going in the positive direction, but the magnitude of that velocity is decreasing. When solving these problems that require the kinematic equation, I like to start with the variables chart. And I will plug in what I already know and what I am looking for. And we know the VI is V naught. We know the V final is 0 because we want to know the maximum height. And the acceleration is negative g because we're making a positive. And we're looking for the displacement. So we're going to look for an equation that has all the variables except t. So the equation that does not have t would be vf squared equals vi squared plus 2a delta y. Now we're going to substitute. And we're looking for h. I'm going to use h as the variable that I'm looking for. When we substitute, we get 0 is equal to v naught squared plus 2 times negative g times h. I'm going to move the v naught squared to the left. You'll notice that the minus signs cancel out, and that leaves us with positives on both sides, and divide both sides by 2g, and we get that the answer is h is equal to v naught squared divided by 2g. Question 3 is a horizontally launched projectile motion problem. An ice block slides off a table of height h with horizontal speed v naught. How far from the table does it land? This is going to be our height h, and what we're looking for is this horizontal distance, which we'll call d. To solve these problems, it's important to define your positive direction, and I'm going to make right positive x and down positive y. The next thing that's helpful is to create a variables chart. This column will be for all the horizontal variables. This column will be for all the vertical variables. And from the question, we know that the horizontal speed is v naught. And the thing about horizontal launch projectile motion problems is to understand that the horizontal velocity is going to be constant because there's no force horizontally. Vertically, there is an acceleration of g because of gravity force is pulling things down. Horizontally, the acceleration is 0. And the initial vertical velocity is also going to be 0 because it's launched horizontally. We're going to set the height of the table as h, and what we're trying to find out is the d, the delta x. Oftentimes, the key to solving these type of problems is to find the time, because the time will link the horizontal motion with the vertical motion. I'm going to solve for the time using the vertical motion because I have 3 of the variables, and I could use that to solve for the time. And I'm going to use delta y is equal to VIT plus 1 over 2 AT squared. And I'm going to use this because I don't know VF and I don't care about VF, and this is the only equation that doesn't have that, and it's got all the variables that I do know or that I am looking for. Now I'm going to substitute, and I'm going to solve for t. And isolating t, we get that t is equal to square root of 2h over g. Now what we're looking for is the horizontal displacement, so we're not done yet, but I'm going to go ahead and bracket that because that will tell me the time. So this value is what would go here on our chart, over there and over there. Remember, it's going to be the same time. Now horizontally, because it's not accelerating, we can use our constant velocity equation, which is delta x equals vx times t. So now we're just going to do a substitution. I'm going to call delta x d. My horizontal distance is equal to v naught, my horizontal velocity, times the time. How long is it falling for? And we just solved that, which is square root 2h divided by g. So the distance is equal to v naught times the square root 2h divided by g. Now we'll take a look at a relative velocity problem. A river flows at speed vr, a boat moves at vb relative to the water. At what upstream angle should it aim to land directly across? All right, first thing we're going to do is to sketch out this scenario. So we have a boat. We want the boat to be able to go across the river, but we're going to aim it at such an angle so that it will end up directly across. Now, the reason you can't just aim it directly across is because the river is flowing downwards at a velocity of vr. And this is going to be theta. So we're trying to find what is theta. What is the angle here that you need to aim the boat so that the boat will end up directly across from the shore here. So we're going to use a little bit of trig. And the big idea is that this Vx right here needs to equal the Vr. They need to have the same magnitude. They'll be in the opposite direction, but if they are the same magnitude, then there will be no change along the x-axis. So the boat would just go directly across. So we're going to use sine theta. And the reason we're going to use sine is because sine theta is opposite, which is Vx, over the hypotenuse. And we're given the hypotenuse, and that's why we're going to use sine theta. And we're going to substitute here. We need the Vx to have the same magnitude as Vr. Okay, so it's going to be Vr divided by Vb. And we're solving for theta. So we're going to take the inverse sine of Vr over Vb. So the inverse sine of Vr over Vb will give you the angle that you need to direct the boat so that you end up directly across the shore. Question 5 is a projectile launched at an angle problem. A projectile is launched at speed v naught and angle theta. Find the total flight time t and horizontal range r. Let's start with a quick sketch and indicate the positive direction. The next step will be to create our variables chart. This will help us organize all the numbers. For the horizontal range, which is what we're looking for, we're going to represent that with a capital R. The horizontal velocity is going to be constant, and using trig, we can rewrite the horizontal, the v naught x, we can rewrite that as v naught cosine theta. And we're using cosine because this is the adjacent angle. The vertical will be v naught sine theta. Let's go and start with the horizontal first. So it's v naught cosine theta, and the vertical initial velocity, because we're using the opposite side of the triangle, will be v naught sine theta. The vertical displacement is going to be 0 because we're looking for the total flight time. It's going to go up and come all the way down. So the delta y is 0. And the acceleration horizontally is 0 because it's moving at constant velocity. And vertically, the acceleration is g. Since we made up positive, the acceleration will be a negative g. With projectile problems, whether it's horizontally launched or launched at an angle, oftentimes the key to solving it is to find the time, because the time for the horizontal is equal to the time for the vertical motion. I'm going to use delta y equal to vi t plus 1 over 2 at squared to solve for the time. And I'm going to use that because I have all the variables, or I have the variables here that I'm looking for. Delta y is 0. Vi is v naught sine theta, and t, I'm going to substitute that with capital T here, plus 1 over 2, and the acceleration is negative g times capital T squared. Now I'm going to isolate t. I'm going to solve for t. You'll notice that one of the t's will cancel out, and that leaves us with the time equal to 2 v naught over g times sine theta. We're going to go ahead and bracket that, and we're going to use that time, and that's the time that would go into this box and this box, and we're going to use that time to find the horizontal range. Since horizontally the motion is moving at constant velocity, we can use our constant velocity equation, which is delta x is equal to vxt. Now we're going to substitute. The horizontal velocity is v naught cosine theta, and the time is 2 v naught over g times sine theta. Now you could stop here, or you can simplify this and use a trig identity. The trig identity states that sine 2 theta equals 2 sine theta cosine theta. If I divide 2 on both sides, I get 1/2 sine 2 theta is equal to sine theta cosine theta. Now what's interesting about that is in this equation right here, we have cosine theta and sine theta. So first, let me combine the v naught and the 2v naught over g. So I get 2v naught squared divided by g. And then now, instead of cosine theta, sine theta, I can write 1 over 2 sine 2 theta. And then the 2 will cancel out. That leaves me with v naught squared divided by g times sine 2 theta. And that is our range, which is what we're looking for in this problem. In this last problem, we're going to look at a projectile problem that's thrown straight up. However, there is a vertical displacement. Question 6. A basketball is thrown upward from height y0 with speed v0 and hits the basketball hoop at height y1. Find the total time of flight t. Let's start with a quick sketch and define our positive direction. So here we have the ball that's launched from v0, it goes up into the air, comes back down, doesn't quite get all the way to the ground, and it hits the basketball hoop, which is above the ground, and we want to find the time that it's in the air. We're going to once again start with our variables chart. We're going to write down what we know so far. So what we know so far is that the ball is launched up with a speed of v0, and it hits the basketball hoop at a height of y1. So the change in displacement will be y1. And because this is a projectile motion, we know that there's an acceleration down because gravity is pulling down on the basketball. And since up is positive, our acceleration will be negative g. And we're looking for the time, so we'll put a question mark right there. To solve this problem, we're going to use our kinematic equation that has the variables that we know and that we're looking for. So the one we don't know is v final. So if we find an equation that does not have v final, that's the one we're going to use. And that equation is going to be y final is equal to y initial plus v I t plus 1 over 2 at squared. We're looking for t, so we want to isolate. We're going to start with substitution. So our final y is going to be y1, and y initial is going to be y, we'll call that y naught, and v initial is v naught times t plus 1 over 2. The acceleration is negative g times t squared. So what we're looking for is the time. And notice that we have t and t squared. So we're going to have to use the quadratic equation. Our game plan here is to move everything to one side and then set it equal to 0. Now we're going to use the quadratic equation. The a will be g divided by 2. The b will be negative v naught. And c will be y1 minus y naught. Now we're going to substitute that into our quadratic equation. And we're going to solve for t. And we find that t is equal to v naught plus square root v naught squared minus 2g times v times y1 minus y naught divided by g. And you'll notice that I didn't use the negative sign here because the negative sign here will give you the value for the ball on its way up. The positive will be for the ball on its way down. So we want the total time for it to go all the way up and then back down hitting that hoop. So we're going to use the positive sign. If you found this video helpful, check out my next video where I solve 6 dynamics problems.